Hey, let's say hypothetically that you are on a SpaceX Starship heading to the moon. And the question is, how close do you have to get to the moon before you have entered the moon's zone of influence? That is, how close do you have to get to the moon before the moon's gravity pulls on you stronger than the Earth's does? And so let's tackle that question. Earth has a mass of 6 times 10 to the 24 kilograms. What that means, this is scientific notation, that means 6 and then you add 24 zeros, or really technically you're moving the decimal point that many places. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That number of kilograms is the mass of the Earth. Now the mass of the moon is about 1/81st of that. 7.4 times 10 to the 22. I'm not going to bother writing that out, but take this decimal point, move it 22 places to the right, filling in zeros, and that gives you the mass of the moon. It is still a huge number, but only 1/81st the mass of the Earth. Now, gravity depends on the mass of these things. In fact, the force of gravity, Newton's law of gravitation, is if you have two objects, m1 and m2, and they are separated by a distance r, we'll call it, then the force of gravity between those two, they're pulling on each other with a force of gravity that's equal to their products divided by the distance between them squared. So that's the general law of gravity between two objects. Now in this situation, we've got 3 objects. We've got planet Earth, we've got planet Moon, and we have a spaceship on the way, somewhere on this line between them. And the Earth has more mass, therefore it's going to have stronger gravity. So our point is going to be closer to the moon than it is to the Earth. You're going to have to get closer to the moon before its gravity equals the gravity of the Earth. So I'm going to call it this point here, just for the sake of argument, and I'm going to say that that is a distance from the center of the moon, and we'll call it x. And so if this is our little spaceship here, I'll say its mass is ms, and it's being pulled towards the Earth, and it's being pulled towards the moon, and this position, x kilometers away from the center of the moon, is where these two poles are equal to each other. And if you're closer than that to the moon, then you are in the moon's zone of influence. So let's go ahead and do the math here to try to figure out what that distance is. And so the force of gravity between Earth and the moon, I'm going to use a capital M for the Earth's mass. And so big G, mass of the Earth, times the mass of the spaceship, divided by the distance between these two. So I need to define what is the overall distance between the Earth and the moon. So this distance from the Earth to the moon I'm going to call d, and that, by the way, is 385,000 kilometers. So the distance from the Earth to our balance point, our gravitational balance point, is going to be d, the full distance, minus x. So d minus x squared. And that is equal to big G times the mass of the moon times the mass of the spacecraft over x squared. The g's cancel. They're on both sides of the equation, so we can cancel those out. And the mass of the spacecraft does not matter either. And so now we have the mass of the Earth over the distance from the Earth squared is equal to the mass of the moon divided by the distance from the moon squared. And let's do a little bit of algebra. We've got big M times x squared is equal, I'm multiplying both sides by x squared, and that is equal to little m times d minus x squared. And so this way I don't have any fractions anywhere. Now I'm going to go ahead and I'm going to multiply out the d minus x by itself. So that becomes d squared minus 2 dx plus x squared. We still have big M x squared there on the left. And so what I'm going to do here is multiply the little m times everything here. So little m d squared minus little m times 2 dx plus little m x squared. And that's big M x squared. Okay, moving over to here, what I'm going to do is I'm going to group the x squareds. So I'm going to subtract little m x squared from both sides. So that's going to give us big M minus little m x squared on the left. And then I'm going to add this and 2m dx to both sides. And so we're going to have plus 2md times x and minus md squared. So I've now moved everything to the left-hand side, leaving nothing on the right-hand side. So equals 0. And so there is a value of x for which this is true. Now this equation is a quadratic equation. We have something times x squared plus something times x plus a constant equals to 0. And so we can use the quadratic formula to solve for x. And if you've had algebra, the quadratic formula, it's that negative b plus or minus the square root of b squared minus 4ac all over 2a. So if that sounds familiar as the quadratic formula, this is a situation where you need the quadratic formula to solve for x. And when you go ahead and do that, you end up with x is about 38,500 kilometers. And that, coincidentally, is about 1/10 of the distance from the Earth to the Moon. And so I didn't quite draw this to scale. It should be significantly closer. Our magic point is about 1/10 of the distance from the Earth to the Moon. So let me just go ahead and move that label over to be about 1/10 of the distance, roughly. Okay, roughly. And so that's how close you have to get to the Moon. The Earth's radius is about 6,400 kilometers. That makes the diameter of the Earth almost 13,000 kilometers. So this is about 3 Earth diameters away from the Moon. And again, I've very roughly got that to scale, on the diagram. So this is how far you have to get to the Moon before you are gravitationally pulled harder by the Moon than you are by